Hi, everyone, and welcome to Webinar Wednesday. We're glad to have you with us for today's presentation featuring Eric Wickstrom, Training Manager of RTI Group. Eric will discuss possible ways to reduce the downtime of CT scanners due to quality control or preventive maintenance activities. Webinar Wednesday would like to thank our sponsor, RTI Group. RTI is a world-leading manufacturer of quality assurance solutions. In 1981, they invented the first X-ray QA system for diagnostic radiology. Since then, innovation has been at the heart of their corporate philosophy, and they have pioneered many QA procedures. RTI continues to invest heavily in R&D to push forward to the very edge of X-ray QA across all modalities. For more information, please visit rtigroup.com. A few announcements before we get started. Please don't miss our 20th anniversary celebration at MD Expo in Atlanta next month, April 11th through the 13th. MD Expo strives to provide healthcare technology management professionals with a unique, intimate, and rewarding conference second to none. You can find all the details and registration at mdexposhow.com. As I mentioned earlier, our speaker today is Eric Wickstrom. Eric, you may begin whenever you are ready.
Well, thank you very much, Jennifer, for this opportunity to share some information and hopefully shed some new light on ways to simplify measurements for CT when we're looking at CTDI measurements, as well as CT dose profile and the beam width measurements. But that's the topic for today. We'll be, like always, ending up with a section of Q&A if there are any questions. So whatever questions you have, please let us have them towards the end of the presentation. Just like to start again with a brief presentation of the RTI Group, so you know where it's coming from. We're a Swedish company based up in Sweden in the north in Scandinavia. We're in the west coast of Sweden, just outside Gothenburg, in a smaller town called Mölndal. We do have a sales office in Singapore that handles the APAC region. And of course, an office in North America, which is in New Jersey, in Tuaco, where we have also sales as well as service and calibration facilities. And just a bit of the history, like you heard from Jennifer, RTI was started in 1981-82. We saw the first non-invasive KV meter on the market. It was the DGX, which you see in front of you right here. And as you see from the beginning, there was not only hardware but also software. And at that time, that was very sophisticated software and very sophisticated computers, the laptop of the day. Moved on into the 90s with more compact meters for kV and also for dose, integrating both radiography and mammography measurements as well. Then moving along into the 2000s, we saw the advent of the multi-probe meter, first X-ray measurement system for multiple probes at the same time. It was the Barracuda system that saw the dawn. That was quite successful, and we are then trying to launch, or wanted to launch, a more portable and more compact instrument, and that was the Piranha, which you see to your right, which is then a variant of the Barracuda MPD, the multi-purpose device. So with the Piranha, you could, in one exposure, capture kV, dose rate, HVL, total filtration, and of course exposure time for radiography. To that, there are possibilities then to attach different probes, and we'll see more of that in the future. So that was in 2006 that Piranha was launched onto the market, and was followed then by a bunch of other products that we now have in our portfolio. So we have a Piranha family. It's the black Piranha that we call it today. It's a family of Piranhas which cater to different modalities. Everything from multimodality, which includes mammography, rad, fluoro, CT, dental, and then the other combinations of that. For instance, a Piranha Mammo that does only mammography, Piranha CT that targets the CT market, Piranha Dental, which is of course targeting the dental market. At the bottom you see the Cobia family, which is a slightly simpler device, although it does have a built-in display. It's for radiography, fluoroscopy, and dental only, and so it has a slightly on the lower segment there. So we cover a wide range of applications. What ties it together is a software that we call Ocean, that is then the readout system for both the Cobia and for the Piranha. So with that, we can also build in information about making analysis of the measurements that we do, create reports, etc., for best traceability. To the right side, we have a number of probes that we then can use to work in different ways and create measurements for certain modalities and applications. And the latest one is the scatter probe in the middle, which is then used for scatter and leakage measurements. So the scatter probe was then launched just a year ago, and it has the stipulated sizes that match the international standards. So it's 100 square meters and 10 square centimeters active areas for measurement. So over the years, we've had maintained and built relations with many of global customers and known names, where we help them both on their R&D side as well as on their field service side with instruments and solutions for their preventive maintenance and service crew and work out in the field. So what do we have then from customers? The feedback that we get, well, we try to focus on fast calibration service. We know that that's a critical issue in many cases. Having people stranded without their instrument is not something that we would like to see. So we focus on fast calibration, turnaround time of typically 10 days in the field. We offer a 2-year calibration cycle, also a priority with many customers. Again, it affects people then for in a positive way. They don't need to be without their instruments every year. We recommend every 2 years for that. And there's also a warranty extension program. If you keep the 2-year calibration cycle, you can then extend the warranty up to about 10 years. And after that, we think it's maybe a good idea to buy a new instrument. Why not? And of course, we have a support team for which we get quite good reviews. They're very responsive. We have support teams both in Europe and of course in the Tobacco office. So there's almost 24/7 coverage. All right. So today's topic is about CT, computed tomography. And the history, of course, I'm sure you know, it was invented in the 70s, early 70s, by Mr. Godfrey Hounsfield, who was awarded the Nobel Prize for it in '79. So in '75, he managed to together with co-workers, launch the first full-body scanner. The first steps were in the early '70s was a head scanner to prove the functionality. Of course, that's had some limited functionality, and that has, of course, grown over the years, so that we have not only full bore or big bore CT scanners, we also, of course, have wide beam CTs, like we see here in this area here, where you have 160 millimeters slice or beam width for that kind of CT, which is becoming more and more common. Of course, at the beginning, you had sequential axial scans in the first versions of the CT scanners. You'd make one slice, advance the table, make one rotation, advance the couch or the table. But then with improving detectors and also improving computing power, we could move into a helical scan. So with a spiral scan, moving the couch through the gantry while scanning. So you'd get a helical CT image. So that's where we have most scanners today performing helical scans in normal patient modes. There's one exception, or a couple of exceptions. The CTs with the wider beams up to 160 millimeters, the couch will then not move for collimations larger than normally 80 millimeters, something like that. Probably, I guess, because table speed would be too high if you have a pitch around 1 or something like that. So for collimations above 80 millimeters, the table is typically stationary. All right, so we are looking at some typical measurements that are being made for constancy checking and also for acceptance testing and etc. So one is the CTDI, that's the CT dose index, and it's done, so I'm sure most of you know, using a phantom that's made out of PMMA, plexiglass. There are some that may be nested, like the one you see in the picture here. Then that's combined body phantom, which has a diameter of about 32 centimeters, and nested into it is a 16 centimeter head phantom, also of the same thickness. And both these phantoms will then have holes in them, so that you have the possibility of measuring in 4 peripheral holes and 1 center hole. Of course, if you have a nested phantom, you only have 1 center hole, of course. Each of the holes here are plugged with sticks made out of PMMA as well, and that's then to fill the holes in here, so you have that we have a more homogeneous phantom for so that it scatters the radiation in the way it's supposed to. All right, so the definition, original definition of CTDI, or CT dose index, is that we want to integrate the dose in the center hole, all of the dose, really from -infinity to +infinity, to wherever it is. And then to get the CT dose index, we need to divide it by the collimation, the number of slices and the thickness of the slices. That's the division that we need to make. So this is the definition of the CT dose index variable. But what has happened, and what happened quite early, was that to measure this, the CTDI in the phantoms, they used ion chambers with an active length of 100 millimeters. That means that anything beyond 100 millimeters, of course, couldn't be measured. So the CTDI 100 was introduced, which is then an integration from -50 to +50 millimeters, and integrating the dose over that area inside the phantom and dividing it by the collimated beam width, the number of slices plus multiplied by the slice thickness. So that was the first step. That was okay, of course, when collimations were quite narrow, from 1 millimeter up to 2, maybe 3, 5 millimeters. That was quite okay. The scatter inside the phantom wasn't all that wide. All right. So, but then as we have other challenges, we won't go into those today, but it touches the subject that we're on. That when you have collimations and beam widths larger than 40 millimeters, you have a problem with the formula that comes in here, because the scatter generated will go beyond plus and minus 50 millimeters inside the phantom. That means that there will be dose tails inside the phantom that cannot be measured. So that's a bit of a challenge. By using this method, an 100 millimeter ion chamber that saturates after quite soon after that beam width. So there are other methods to calculate CTDI beyond those widths or beam widths above 40 millimeters. I will talk about that later on. We'll now assume narrow beams. All right. So CTDI is one thing, CTDI 100 is another thing. CTDI weighted CTDI was then also introduced to take into account also the effect we had from the on the skin. Not only so the phantom simulates a body. So inside you have the center measurements is then inside or organ dose or penetrated dose. But it's also interesting to see here what happens at the skin level or just below the skin level. So here we've got holes at 10 millimeter depth from the surface to emulate or simulate the dose absorbed through the skin. So there's a formula then looking at this, taking into account the dosage, the CTDI in the center hole, and the CTDI of each peripheral hole, or rather the average of the CTDI 100 in the peripheral holes. So because it's weighted, because then the CTDI weighted value looks more at has a higher weight to the skin dose, so to say. And the way it's done is, of course, we look at the dose here, CTDI 100 with the pencil ion chamber in the center hole, make one axial scan and not moving the table, and making a scan and integrating the dose. And that's if you have a pencil ion chamber, you just read the dose value, of course. From the peripheral holes, we do the same, and just in the peripheral holes to get that done. So those are the formulas. So and that's the CTDI weighted. To get the CTDI volume, that's usually displayed on the CT scanner console. Takes into account also the pitch. So if we have a movement in there, it's the CTDI weighted divided by pitch. So these are all standardized formulas that are used in the industry. So there's no news in there. What is that? How is that done then? Well, the method is using a standard pencil ion chamber like this one, and a phantom, and then collect the measurements. If you have a formula or a software to gather that information, it's quite easy. You just need to know which position are we in, and then take the measurements. Of course, we need to know what the slice thickness is and the number of slices, because that was in the formula, of course. Then we can take the values and compute and calculate the CTDI values and CTDI weighted. And if we know the pitch, of course, we also have the CTDI volume. Now, with this method that has been around since mid-80s somewhere, and which was designed for narrow beam CTs, there are some efficiency implications that that we encounter today. Well, because there are some uncertainties that are introduced when we're doing an axial scan, one axial scan. There could be an over rotation of the tube, that it does more than just one revolution, and that could have an impact on the accuracy of the measurement. The exposure time could vary as a result of the over rotation, or as a separate impact. And there could be variations in tube exposure start position. So if this tube starts firing in different positions around the rotation, and that could also have effects of this. And what we mean with over rotation is something like this. We have the tube beam here in yellow, the phantom in the middle of the gantry, and we rotate it. And this is the way we're hoping to have one axial scan. It's 360 degrees. Now, if we have over or under rotation, we might end up here if it's 340 degrees, or we might end up here in another situation when we have an over rotation at another in a different number of degrees, other end position. So that's one possibility. We had the opportunity a couple of years ago to measure on a standard machine, which is out in the market. I won't say which one, where we found that there was an over rotation or over exposure. We thought it was an over rotation, but we found that the additional exposure time was 45 milliseconds, and it was constant, regardless of the rotation time. We had a 45 millisecond additional exposure. Now, if we weren't aware of this, we would end up in a situation where we'd have an additional 4.5% of dose if the rotation time is 1 second. If we have a 2-second rotation time, of course, it reduces the problem with half, and that's 2.25% then error or additional dose, which really shouldn't be there. And if we have a 0.3 second rotation time, we have now these quite fast CTs. 45 milliseconds was still the additional exposure time, and in a total rotation time of 0.3 seconds, that's a substantial part. That's 13.5 seconds additional. That's 13.5%. Sorry, additional radiation introduced through over rotation or additional exposure time. So if we know about it, that's fine, but if we're unaware, this introduces uncertainties in the data that we collect. And if we do one visit, one check, if we use one rotation time in 1 year, come back 6 months later and do it again with another rotation time, we might find that the data doesn't match. And if we're unaware of these 4.45 millisecond additional time, rotation times, we might have a problem and data that don't really match, so they don't correlate. So this is quite important in our aspect. So, and this is for measurements made in the center hole of the phantom. So there's still a symmetry to it, and we're getting data that that we don't expect every time. So that's one issue that we found during this testing. Another thing we found was that we had an effect also when measuring the CTDI in the peripheral holes, gathering data for the CTDI weighted CTDI. And of course, measuring in the peripheral holes, that's what we want to do. And what happens when we do, and why we want to do it, is that the distance from the tube itself changes, so the dose rate will change due to the distance, for one, but also due to the added attenuation and scatter generated inside the phantom. So we'll have a non-constant dose in the peripheral holes. If it's in the center hole, of course, it's symmetrical, so we should have a constant signal output from the pencil line chamber. In the peripheral hole, it will vary depending on the position of the tube, and of course that has to do with the distance, the dose rate in that measurement situation. And if we have an exposure that starts here, pencil ion chamber right in this position, well, of course, you'll have another pattern where you have here starting with not the maximum dose rate, it's less than maximum dose rate, and it's only when you've rotated the tube 270 degrees, where you reach the maximum dose rate for this measurement example right in this position. And then it goes back to something less than maximum, but it's more than the minimum value. The minimum value, of course, is when you have the tube in the position just opposite to your dose ion chamber. Now, this is what we found in that same machine that had an exposure time of 45 milliseconds. It appeared that we did 3 measurements, 3 scans, leaving the dose or the CT ion chamber, CT ion chamber in the same hole, and repeated, just made 3 consecutive dose scans or CT scans. So the first one was over here. It's nice, and here you see, of course, this is the maximum when the CT ion chamber, the hole with the CT ion chamber, is closest to the tube, and then it tapers off and goes back. So we had here the second dose, but it's in the same hole. We just repeated the scan, and we get a different position of the peak, slightly different. The shape of the waveform is the same, but the position is different. And here is this third one, where we have a double peak on it, which is kind of odd. Now, this tells us that the tube starts to fire in different positions. And you may think that, well, maybe that doesn't do very much. Maybe it evens itself out because it's a circular motion. Well, since we have contribution both from the position and the over rotation, probably, we see that we have 3 different values, these 3 consecutive scans. First one being 19.5, and then 19.8, and 23.7 milligray centimeters. That's the values that we've got. Looking at the difference here from the first scan to the third scan, the difference is 21.5%. And this is then only doing 3 consecutive scans, changing nothing, just repeating the scan, the very same settings, everything. But we get 3 values that vary as much as 21.5%, which is quite interesting. Now, we're talking about the CTDI weighted, and that's the one we look at. How does that impact it? Well, it's we have the measurements from the peripheral holes, which can vary up to 21.5%. Even if it's only 2/3 of it, it's still substantial error contribution to error or uncertainty in this. One CTDI weighted value could vary as much as 20%, only depending on how the tube fires. Okay, so that's a bit of an uncertainty. What are we actually measuring? What are we looking at, and what are the effects? If we then take a step back and look at what it comes from, well, we have the exposure start error, which is then in the peripheral holes. That's the one. Then we have also the CTDI 100 in the center hole, which is affected by over rotation. So there we've got an additional or contribution of 4.5%, even up to 13.5% for the center hole. Of course, if we add up and do all the math, we're still maybe at 20% off between two CTDI weighted measurements, where we have the pass-fail limits typically at ±20. So we're pushing the limits here a little bit when looking at this kind of thing. So we have a look at the uncertainties that we found. Well, we might have, if we say you do a 1 second scan time, we might have up to 4.5% error or difference or uncertainty. From the varying exposure start, well, we might have as much as 21.5. And what does that do then? And what can we do to change that? Well, here we can reduce that 4.5% by reducing or increasing the rotation time. As we saw by scanning in a 2 second, giving it a 2 second scan, we're down at 2.5%. So that would be one way. How about the exposure start? Well, the only real way would then be to making multiple exposure in each position and getting the average out of that. And at the same time, hoping that that is the solution and that's the way to go. That we in that way, we'll get a decent or a stable value for that. And then the question is, well, how many exposures do we need? Are 3 exposures enough? 5? Or how many do we need to get a statistical background and a statistical safe average value that we can then feel confident of using? That's quite interesting to figure out. All of these two things then will contribute to increasing or prolonging the test procedure that we're doing. Each exposure then, a minimum of 5, of course, 1 in each peripheral hole and 1 in the center. So that's a minimum. And making how many, if it's 3 or 5 in each of the peripheral holes, we're up to 15, 20, 21 measurements before we have something that's that we consider kind of safe. So that's a contribution. Do we have that time to spare? Well, that's maybe, but are there other methods which we can where we can work in a smarter way? Well, there is a tool called the CTDOS profiler, where we have a sorry, let's see here. We've got at this point here, we've got a point dose detector. It's a silicon chip, 0.25 millimeter big, right in this point. So it's actually a point dose detector. It does look like a pencil iron chamber. It has the same shape, the same form factor, in order to fit into the holes in the phantom. So that's why it looks like it. But it is an aluminum skin right here for filtration purposes. Inside it's filled with PMMA, and here, right here, there in the middle of it, we have this silicon chip for dose measurements. It goes into a phantom, and it goes into the center hole. We make a helical scan, not the axial scan, but we make a helical scan, one exposure, and that's enough. And this is then a simplification, a simple diagram of what happens here. Since we're doing an axial scan, we're moving the phantom with the CT dose profiler in it through the beam. So then the CT dose profiler is then designed so that the point dose detector is in the center of the phantom at 75 millimeters from each of the edges of the phantom. All right, so we then fire up the tube. As soon as the beam starts hitting even the edge of the beam, scatter is generated inside the phantom, and the CT dose profiler detects that. As it moves into the center of the beam, we reach the maximum, of course, of the dose at the center of the phantom. And as we push through and leave the phantom, it tapers off and goes back into to zero as the phantom leaves the beam field. So it would look something like this if we try to animate it. It pushes through and then it rises, and as it goes through, we have data about it. So we use the CT dose profiler in a way where we scan the dose. We sample the dose in the center of the CT dose profiler, which is in the center of the phantom, with a known sample frequency. If we know the speed of travel through the beam, we can then recreate the shape of the dose profile inside the phantom. And when we do, we realize that, well, this is actually the integral of dose inside the phantom from -infinity all the way through zero up until +infinity. So what we actually see here, thanks to the sampled dose values here, we can integrate the whole area below the curve, and that will then be the CTDI value as defined in the standard CTDI. And it's from -infinity to +infinity, since we capture everything, all the dose tails. To get the CTDI 100 value, we need to truncate the tails, and very interesting information here that it lies outside the ±50 millimeters that fall outside the CTDI 100 formalism. So how do we do the calculation of CTDI weighted then? Well, with the CT dose profiler, we'll get the CTDI 100 in the center hole. We get that with the CT dose profiler during the scan. But we need to get something from the peripheral holes. And instead of relying on a method which we've seen can vary quite a lot, we rely more on empirical data that we've collected from manufacturers and other end users of different machine types that will give us a formula so that we can calculate the CTDI 100 based on the measurement in the center hole. If we know the scanner type, we know the KV setting, we know what generator it is, and the phantom, the type of phantom, if it's a body or a head phantom, we can then calculate this value and get us a CTDI weighted model. Now, this peripheral CTDI 100 peripheral is calculated, and we use the known relationship that we have that we've gathered from thousands and thousands of scans on those typical machines. So we do this calculation with using statistical data, which is a big statistical base of data. Not only 3 exposures, not only 5, but thousands of measurements that we base that on. And we do 1 exposure. We don't need to do 5 even. We don't need to do 10. We don't need to do 15 or 20. We rely on 1, and that's the way we can save time in this way. So how does that affect the efficiency? Well, we reduce that by, well, the 4.5 seconds. Of course, we can work with that. Variations of the exposure start, well, it doesn't really compute. For the 4.5 seconds of over rotation, if there is one, if we increase the number of rotations, we only have 1 contribution at the beginning of the scan for each scan. So if we make several rotations, that will of course then reduce that contribution. And the contribution from varying exposure start, well, that's eliminated because we're exposing only in the center hole where we have symmetry and there's no influence. It doesn't matter where, and on the rotation, the tube starts firing. So we can get rid of that. So summary for the CT-dose profiler is that we measure the full CTDI for infinity, including the tails. We truncate the data to get CTDI 100. So we need to scrap some data to get to CTDI 100. We, based on a big statistical background database, we then calculate CTDI weighted and CTDI volume. Of course, we know that since we know the pitch, and we get a graph, as you see here, of the full dose profile of the scan. And as you can see here, it goes up, and there's a little bit of a notch here, and that is when the tube goes underneath the headrest or the couch. So you get the table or attenuation from the headrest or the couch. That's why you have a drop in dose rate in those areas. So you can actually then see graphically what kind of data do we have. And does it look good or doesn't it look good? We also see if there are tails in here and how they affect the measurement. All right, so that's one way of speeding up CTDI measurements. And of course, you can use both, one and then benchmark with the other, and use the one-shot method with a CT-dose profiler to save time as a constancy check. What you need is one scan with a phantom, and that's reasonable, and that's easy to get in between patients. Now, looking at the CT beam width, which is also called for in quality checks. Also, of course, when it comes to maintenance jobs, to make sure that everything is the way it should be. We have a traditional method, one of them being using X-ray sensitive film, which you need to position, of course, in the ISO center, and you make an exposure, and there is some blackness on the film, and that is then the width of your beam. And that's one traditional way of doing that. Now, what kind of impacts do we have? Well, you need to find a setup without backscatter, so you get a clear indication, that you get a clear signal, clear darkening of the film. So that's the first step. You need to set up a suitable scan mode if it's just a scout or a pre-scan to get that done, and then you need to set it up for that. Sometimes it's easy. Some scanners are more tricky to find that suitable scan mode. And we need to evaluate the exposure of the film. What does it look like? Well, it's a grayscale, It goes from nothing to dark, and somewhere along that grayscale, you need to find the position of what is the full width half maximum in that on that film, on that exposure. Of course, you can do that and estimate. There was a scale on it, but where is the full width half maximum? That's something that we need to figure out. There's a question here about reproducibility. For 2 different scans, how do you compare it with the previous film? What is the reproducibility? How sure can you be that you're actually you're doing the right evaluation 2 times in a row? And of course, you can then use a scanner to scan the film and automatically, or with the help of that scanner and software, evaluation software, eliminate some of that in what do you call it, human error in an evaluation of film exposure. So that's something we can do. And these things are quite important, I think, because you have a risk, especially when you have narrower beams, 10, 20 millimeters. If you have an overbeaming of only 2, 3, 4 millimeters, that's on each side, that's a substantial amount of overexposure. If the detectors only need 10 millimeters of X-ray beam, but you're over beaming with ±4. That's 4 on each side. That's 18. That's 80% of the extra dose that the patient gets. And I think that could be interesting to be more precise when looking at that kind of exposure without spending too much time. All right. So there's an alternative method. Again, we look at the CT dose profiler, and the name is CT dose profiler because the prime objective of it is actually to look at the dose profiler in CTs. So instead of using it in a phantom, we now use it free in air. So as we said before, it's a point dose detector. It's omnidirectional, so it's symmetrical when it catches the dose. It's very high sensitivity. It's a silicon chip, very, very strong signal response and very, very quick signal responses, step response as well. And the method then would be something like this if we illustrate it. We've got a beam, the CT dose profiler. There, it looks like a pencil iron chamber, but remember there's a point dose detector planted in the middle, smack in the middle of this detector right there. So there's one sensor that we have in place. The thing we need to work on is we need to know the speed of travel. But of course, if it's a CT, if we then position it here, poke it out of the end of the phantom, so it hangs free in air outside the edge of the table. We know the table speed, so we can use the position it on the table and use the table speed for our calculations. Because we know how often we sample the dose, how often we measure the dose, and that's usually at like 2 kilohertz, something like that. And if we have the speed of travel and the dose, the sample rate of the dose, we can then recreate the dose profile and to scale as well. And this is something what it would look like. We poke it through the beam, and it will then follow, and that's the signal we get from the chip, the response. And through that, we can calculate and get the full width half maximum, since we know the speed of travel and dose rate, etc. With the graphical analysis inside the software, it then computes the full width half maximum to the fraction of a millimeter. It also gives us the CTDI, free in air, of course, because that's what we're doing. It's the integral of dose in free in air. And the software also has a function that gives us the geometric efficiency of the beam, so we can feed that information back directly to the operator. Now, this is then a way which is easy to fit and to work with, and it gives you a quick response. So it gives you the true beam width, free in air, recreates the dose profile, so you can have a check of the geometric efficiency, and as well as the CTDI free in air. And this is the response that we get from the software where we have all that information. The beam width, we can see the heel effect, what it looks like. The geometric efficiency is calculated based on the collimation. We see here it's a 60 millimeter collimation, but we get a beam width of 63.0 millimeters, which is quite precise. Here's also interesting that thanks to the sensitivity of the silicon chip we have inside here, the point dose detector, we can work out quite precisely how the dose profile looks and where the full width half maximum is to give us that, with a high degree of repeatability. For wider CT beams, when the table, we were talking about the couch, or the table is not moving, we then need to poke the detector through the beam. If the table isn't moving, we can then use another Lonnie mover, which is a moving device, has a servo motor, high precision servo motor with up to 300 millimeters per second speed. So it will then push this rod, this holder, which is carbon fiber, so as not to generate too much scatter. Put this one on the couch, and it will then poke it through the beam, and we at a known speed. We know then the speed of the sample speed, and we get a dose profile out of that. All right, so how does that help us then? Well, it's positioned free in air beyond the edge of the table, easy to get a good position without having any backscatter, of course. We don't need to, we can't prop it up on anything, and we can use the phantom and use that as a holder for the CT dose profiler. It uses normal helical or spiral scan modes, patient mode, whatever you find. You don't need to go in the service modes at all. The result, immediately after the scan is completed, you get the precise, so there's no time wasted trying to evaluate it optically. You get it precisely upon the completion of the scan. This gives us also then a high reproducibility of the data. That means that the data that you collect will correlate with what you had in previous measurements in previous times. And this is finally then a setup of the this is it. There we go. See, that's it. Pokes through the beam. I'll do that again so you can see. It's then set up. We've got the mover set up right here, so that we position it outside the table, so it's free in air, no backscatter, nothing that disturbs it, and we then poke it through at the known speed, and the software will then gather that information, that data, and it then gives us the beam width. We can zoom in, have a closer look, and get all the data for the beams. Also for smaller beams, of course, we get other data, but again, always very precise and with high resolution. And that the method in itself also gives us a very high reproducibility of the data on top of this the speed of execution. So yep, that was it. Just a repeat there. So that was the basis of it. There are traditional ways of doing CTDI measurements, for which we have alternatives. We can offer both methods, of course, for those who want both suspenders and the belt. For the dose profile measurement or the beam width measurement, there's also an alternative method that we can offer, which offers improved efficiency and faster measurements. So with that, I'll open up for questions if there are any.
Thank you so much, Eric, for all of this valuable information. As a reminder to the audience, if you have a question, please use the questions feature on your webinar dashboard. We do have a few that have come in already, so we'll start with those. Our first question is, how do you know how to convert dose in the center of phantom to dose in the periphery?
Well, it's like we said in the presentation, we've gathered data and had help. So we've bought some data, had services to buy data from both from manufacturers and from others who investigated and done research on it. So we then know the relationship between the dose in the center hole and the dose in the peripheral holes. And by that, we can then measure in the center hole and have a conversion factor, a K factor, to give us the data for the peripheral holes, and then we can calculate the CTDI weighted that way.
All right. Our next question is, how can an ion chamber give any kind of resolution of the CT dose profile?
Well, it will struggle, I would say, due to the length of it. To give any sort of beam dose profile or any, you would have to the measurement, the body of the measurement probe needs to be of the same order of magnitude or much smaller than the object it's measuring. So if it's a beam width, it needs to be of 100 millimeters. The probe itself needs to be much smaller than 100 millimeters to get any kind of resolution. If it's 100 millimeters, it simply doesn't really work very well to get any accuracy on that, on the beam width in the case.
Our next question is, I'd like to use the CT dose profiler, but the last time I checked, it doesn't have an NIST traceable calibration, which is required for the state of Michigan.
That's odd, because it should have one. At least when it comes from our labs, it is calibrated, and those calibrations are NIST traceable. So I don't really, there must be some mistake there, because all our equipment leaves the lab with the calibration certificate. Of course, if it's been sent in for calibration, of course. But everything we deliver comes with the calibration certificate. So sounds very odd. We'd like to get in, like you to contact the service or the support team for that, please.
All right. Our next question is, you mentioned a database of many peripheral CTDI 100 with the CT dose profiler compared to center CTDI 100. This relationship would depend on phantom size, correct?
That's correct.
And then goes on to ask, do you need to input phantom size into Ocean when you are measuring CTDI with the dose profiler?
Yes, that needs to be, because the conversion factor, of course, changes with the size of the phantom. Of course, if it's a small phantom, the relationship between the center hole and the peripheral holes would be 1. If you use a larger phantom, the body phantom, of course, that relationship would be different. And it differs also with KV settings. So it's for different KV values. There are different, but there's a table, there's a lookup table built into the Ocean software that we're using. That calls up. So when you select a GE Lightspeed, for instance, and the setting at 120 kV and a body phantom, the software finds that K factor, and all you need to do is set the right table speed, etc., and you get that information right then and there. That computation is done automatically in the background.
All right, and then this is a question along with those, asking, can you share the ratios of the center peripheral for both phantom sizes? And you may have just referenced where to find that.
Well, we use what we call a K factor, so it's more than just a ratio. It's but it follows the formalism of CTDI, weighted CTDI. So the factors that we have there are not strictly a factor like that, but there are ways. If there is a scanner, the Ocean comes pre-programmed with these kind of K factors for most scanners on the market today, and with the KV stations that are applicable for those scanners on the market today. So it goes from 180, 120, 100, 180, 100, 120, 140, or whatever it might be, the clinical range for a certain scanner. There will also be K factors built into Ocean for most of the scanners out there. If by chance there is a scanner that does not appear in that database in Ocean, you might want to update your Ocean software, because they're continuously adding new K factors for different scanner types. If there isn't any, still you can't find the scanner you're looking for in that database, you can make your own K factors, and there are instructions on how to do that available with us. So you can actually, with an ion chamber, you can do that once, measure in the center hole, you can measure in the peripheral holes a number of times, and make that background data collection on your own, if need be. So you do it once, invest that time once, and then after that you can just use a K factor and one exposure, and you're good to go.
Excellent. Well, we do have lots more questions that have come in, but we are out of time. So to our audience, if you did submit a question, please rest assured that those will be delivered to Eric, and someone with RTI will be getting back to you. Thank you so much, Eric, for your time today and for a great presentation. I would like to encourage everyone to visit today's sponsor to learn more about the services that they provide to our industry. Please visit rtigroup.com. A quick reminder that you can obtain your continuing education certificate by completing today's post-webinar survey. The survey will be emailed to you 1 hour after the end of today's webinar. You must complete the survey to receive your 1 CE credit from the ACI, and you'll be able to download your certificate immediately upon completing the survey. If you have any questions, please contact us at webinar@mdpublishing.com. We'll be back next week with another webinar. Please visit webinarwednesday.live for more details and for complimentary registration. Thank you all, and have a great afternoon.
Thank you.